Alright guys, we can now move on to Chapter 5, which is going to be the last chapter we're going to discuss in this class. And Chapter 5 talks about integration. We're starting, of course, with Section 5.1, in which we're going to be talking about approximating areas. Now, before we do that, what we need to start with is a certain kind of notation we use a lot throughout all math, and that is sigma notation. Sigma notation looks like this, and it's where I have a capital sigma, and then on the bottom I have something like I equals A, and on the top I have something like B, and it's going to be of F of that I. So this notation looks really hard, but I promise it's actually not. What this is actually trying to say, if you see a sigma, what that says is it's the sum. This is a sum, which means I'm going to add up a bunch of stuff. What I'm going to add up is I'm starting when I is equal to whatever A is. I'm going to start there. So then I would plug in an A. After A, I would do one more. So like if A was equal to 2, I would plug in a 2, then a 3, then a 4, then a 5, on and on, until I get to whatever B is. So this is like saying the sum of F of I from I equals A to I equals B. So I'm going to start with A. I'm going to plug in A, and then plug in the next thing, and then the next thing, and then the next thing, up until I get to B. Then I'm going to add all of those up. So as an example, let's do the sum from I equals 1 to 5 of 2I. So what this means is I'm going to start by plugging in a 1. So I'm going to do 2 times 1. Then plug in a 2, 2 times 2. Then plug in a 3, 2 times 3. Then plug in a 4, 2 times 4. Then plug in a 5, so 2 times 5. And then I know I can stop there because I'm saying from 1 to 5. So I know I'm going to stop at the 5. So once I plug in a 5 into 2I, I stop. So this becomes 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, 8, and 10. Add all of those up. 2 plus 4 is 6, 6 plus 6 is 12, plus 8 is 20, plus 10 is 30. So again, we are just going to add everything up. Start with a 1, then 2, then 3, then 4, and then I stop whenever I plug in a 5. As another example, let's do the sum from I equals 4 to 9 of I squared. So the same thing here. I'm going to start with a 4. So I would do 4 squared plus, then do 5, then 6, then 7, then 8, and then 9. And I know I stop there because I'm saying from 4 to 9. So I plug in a 4, plug in a 9, and everything between them. Let's add this up. 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, and if you added all of those up, what you would get is 271. So whenever you see a sigma, that's a sum. We are going to add it up. Let's do some more examples. We're going to write in sigma notation and evaluate the sum of the term 3 to the power of I for I equals 1, 2, 3, 4, and 5. So it's saying the sum, which means I'm going to do the sigma. And I know I'm going to add up the terms of 3 to the power of I. So what I need are where I start and where I stop. Well, the first I see is I equal to 1. So we're going to start with I equals 1. And then it's going to stop when I is equal to 5. So now to 5. So this is how I would write that in sigma notation. Now I need to actually see what this is. So plug in a 1 first, 3 to the first. Plug in a 2, that's 3 squared. Plug in a 3, that's 3 cubed. Plug in a 4, that's 3 to the 4th. Plug in a 5, that's 3 to the 5th. 3 to the first is 3, plus 3 squared, which is 9, plus 3 cubed, which is 27, plus 3 to the 4th, which is 81, plus 3 to the 5th, which is 243. Add all of those up, and you get 363. Another example kind of like that. We're going to do the same thing. I'm not going to rewrite all of that. Same thing for the terms of 2 to the I with I equals 3, 4, 5, and 6. So the same thing here. I'm adding up a bunch of terms, so I know it's going to be the sum. I'm starting at I equals 3, and I'm going to end at I equals 6. And my terms are going to be 2 to the power of I. So now just plug in a 3 first, so 2 to the 3rd. Plug in a 4, plug in a 5, plug in a 6. 2 to the 3rd is 8. 2 to the 4th is 16. 2 to the 5th is 32. And 2 to the 6th is 64. Add all of those up, and you get 120. Let's do some more examples, or really just one more example before we move on. We're going to write the sum 1 plus 1 over 4 plus 1 over 9 plus 1 over 16 plus 1 over 25 in sigma notation. So I want to write it as a sum. So how I know what the sum is I'm going to look at here and see if I can see a pattern. Okay. Well, first things first, I know I can write 1 as 1 over 1, right? So let's see if that helps us out. 1 over 1 plus 1 over 4 plus 1 over 9, 1 over 16, 1 over 25. So the first thing I see is that every term is 1 over a thing, right? 1 over this, 1 over 4, 1 over 9, 1 over 16. So the numerator in all of these is a 1. So I know this is going to be 1 over some stuff. So now let's see what this stuff is, okay? Well, my first term has a 1, my second term has a 2 or a 4, my third term has a 9, my fourth term has a 16, and my fifth term has a 25. So I can see my pattern is all of these are squares. 1 is 1 squared, 4 is 2 squared, 9 is 3 squared, 16 is 4 squared, and 25 is 5 squared. So the denominator is I squared, because all of these are squares. So now I've got to think about, okay, where does it start and where does it stop? Well, let's look at what my first value of I is. Well, this is 1 over 1, and since 1 is 1 squared, I know I plugged in a 1 right here. So this is going to be I equals 1. Then looking at my last term, it's 1 over 25, and that is 5 squared, which means I plugged in a 5. So the last thing I plugged in was a 5. That is how I would write this sum in sigma notation. So we have some properties of sums that are going to help us out. The first one is that if you do the sum from I equals 1 to something n, n might be 2, it might be 3, it might be 4, we don't know, from 1 to n of a constant. So if this is just a constant, so like over here I had 1 over I squared, which means I plugged in stuff for I, right? Notice there's no I here. So this is a constant. If you're going to do that, what you're going to end up getting is n times that c. And let's think about why. So if I'm adding a constant, this means I'm just adding c a bunch of times. Well, how many times? I do it once, and then twice, and then 3 times, 4 times, 5 times, up until n, which means I'm adding c n times, which is why I get n times c. Another property we have is if you're doing the sum, the bounds really don't matter here, but I'll just put from 1 to n again, of a constant times something in terms of I. So I'm just going to write it as ai. Pretty much it just means it's a term involving an I. So if you have a constant, what I can actually do is just pull this constant out front. And the reason is because it's not in terms of an I, and I only care about I's here, right? So since this is just a constant, I can pull it out front. Another property that I have is something used a lot, and this is that if you're doing the sum and you are adding or subtracting 2 different terms, what I can actually do is just take the sum of each term and then add or subtract them. So I don't have to look at the whole thing. I can break it up into 2 parts and worry about each part, which is very helpful. My 4th rule is another really helpful rule. I don't have any room right here, so I'm just going to write it right here. If you're doing the sum from 1 to n, what I can actually do is I can split this into 2 different parts by finding a number between 1 and n. So like let's say I did the sum from 1 to 8, I could do something between 1 and 8. So like 4, right? And I could split this into 2 things. So what I mean is I can do like from 1 to something m of ai, and then add, start back up. I stopped at m, which means I'm going to start back up at my next term, which would be m plus 1 to the n. So I can split it up into 2 parts, which sometimes proves to be really helpful. So on top of these properties of sums, something else that we have are some known sums that are going to help us out. So here I already know what the sum of a constant is, so that's helpful. But I can also do know a few more sums. So the first one is if I have a sum from 1 to n of just I. So I would just plug in 1, then 2, then 3, then 4, then 5, blah, 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 up until I get to n. If you add those up, what you actually end up getting is n times n plus 1 over 2. If you are doing the sum from I equals 1 to n squared, of n, of I squared, my bad, what you end up with there is n times n plus 1 times 2n plus 1 all over 6. And lastly, if you do the sum from I equals 1 to n of I cubed, this becomes n squared times n plus 1 squared all over 4. So knowing these known sums here can help us solve some harder ones. So that's what we are going to do now, is practice some harder sums. Example. Write in sigma notation and evaluate the sum of the terms I minus 3 squared for I equals 1, 2, 3, up until 200. So first things first, let's write this in sigma notation. So that means I know I'm doing the sum, so sigma. I'm starting with I equals 1, and I'm going all the way to 200, and my terms are I minus 3 squared. Now, normally to evaluate this, I would plug in 1, and then 2, and then 3, and then 4, blah, 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 and then add them up, right? Well, this is going up until 200. It would take me forever to add all of those up, so we're not going to do that. Instead, we know all of these rules we just learned, so I'm going to use those. Okay. First things first is I need to work out what I minus 3 squared is, because I only know what happens for I squared or I or that kind of thing, right? I don't know what happens if I'm changing I. So since this is I minus 3 squared, I can't use this rule just yet. Okay. So first I'm going to have to actually square this out. If you do I minus 3 squared, we know what you're going to get is I squared minus 6I plus 9, right? Because I would do I minus 3 twice, which would get you this. Well, what we know from the properties we wrote down was I know that if I'm adding up a bunch of terms in here, I can split it up into a bunch of different sums, right? I also know I can pull a constant out front. So I can actually rewrite this an easier way and make it the sum from I equals 1 to 200 of I squared, and then minus 6 times the sum of I equals 1 to 200 of I, plus the sum from I equals 1 to 200 of 9. And what's really nice about this is I know how to do each of these here. Okay. The sum of I squared, we already know, is equal to n times n plus 1 times 2n plus 1 over 6. So let's do that here. Our n is 200. So it would be 200 times n plus 1, which is 201, times 2n plus 1. 2 times 200 is 400. 400 plus 1 is 401. All over 6. Again, I get that from this first term and from our sum of I squared rule here. Then I can do negative 6 times the sum of I. Well, I know the sum of I ends up being n times n plus 1 over 2. Our n here is 200, so this becomes 200 times 201 over 2. Then over here I have the sum of 9. 9 is a constant, and so I can use my rule with the constants right here. Since my constant is 9, I just do n times 9. Well, here our n is 200. So 200 times 9. So now I just have to add all of these up. If you did 200 times 201 times 200 times 201 times 401 divided by 6, you would get 2,686,700. If you did negative 6 times 200 times 201 divided by 2, you'd get negative 120,600. And then if you did 200 times 9, you'd get 1,800. Add all of this up, and you get 2,567,900. So like I said, this was a lot less work than simply adding all of these up, right? Because I would have to plug in a 1, then a 2, then a 3, then a 4, on and on and on, till I got to 200, which would take forever. Let's do another example of that. We're going to do the same thing. Again, I'm not going to rewrite all of that, but the same thing for this time our terms are going to be I to the third minus I squared for I going from 1 to 2 to 3 up until 6. Up until 6. So for this one, again, I'm doing a sum from I equals 1, because I start at 1, up until 6. And my terms are going to be I cubed minus I squared. Well, like we said, I can split this into two different terms. So that's going to be the sum from I equals 1 to 6 of I cubed minus the sum from I equals 1 to 6 of I squared. Well, luckily, I know these, right? This comes from our rules we have. The sum of I cubed we know is equal to n squared times n plus 1 squared over 4. In this case, our n is equal to 6. So this would be 6 squared, which is 36, times n plus 1 squared, which would be 7 squared, so 49 over 4, minus, and then the sum of I squared we know is n times n plus 1 times 2n plus 1 over 6. N here is equal to 6. N is 6, so n plus 1 is 7. 2n is 12, plus 1 is 13, all over 6. If we do 36 times 49 over 4, that's 441. And then if we do negative 6 times 7 times 13 divided by 6, that's negative 91. 441 minus 91 is 350. So that is what sigma notation is. We are going to see this a little bit in section 5.2 and then again a lot in calculus 2 whenever you go on and take that class. Okay, so now that we understand sigma notation, I can actually get into the root of what chapter 5 is trying to do. What chapter 5 is trying to do is we're going to look at a graph, and let's say I have a random curve. So I'm just going to say this curve. This is the graph of f of x. What I want to do here in chapter 5 is I want to find the area of the region bounded by these two lines. This is what I want. I want to know how much space is inside of here. Here in section 5.1, I'm going to start by just seeing if I can get really close. Okay? Because we haven't quite learned just yet how to find what this actually will be. So I'm going to try and get as close as I possibly can. Okay? So let's think about how I can do this. I'm just going to redraw this curve right here of f of x. What I can do is I can actually split this into parts. Okay, I can split this into smaller parts instead of trying to look at this whole thing. How I can do that is think of a shape that's easy to find what the area is. Okay, well, I can do that with a rectangle. Because I know the area of a rectangle is just my length times my width. Okay, so let's start there. But what I want to know is how high do I need to actually go? Okay, so how I'm going to start is by using every left point. So let's say I'm splitting this into a region like this. I'm starting here at point A, and then I'm going to start here, or then I'm going to stop here at point B. And let's say I want to split it up into regions like this. Okay? My first way is I can look at the leftmost point. So right here, this probably wasn't the best graph to draw to illustrate this. Let me draw a different one. Let's do this. And let's say I want to go from A to B here. And I want to split it up. Let's do that. Okay. So I'm going to start with my left my left point. So for this first part of it right here, for this first chunk, ignore everything else. For this first part right here, I'm going to use the leftmost point, which is going to be A. So I'm going to find that. That's going to be my height, and here we go. So the area of this is going to be my length, which is this right here, times my width. Okay. So my length is going to be whatever the function is at A. That's my height, right? And then my width right here how I find that is it's the length of each part, right? So let's think about how I got that. My total length is going to be b minus a, right? That's going to be my total length. So for each part, it depends on how many parts there are. So it's going to be over how many parts I have. So my width is going to be b minus a over n. I'm going to do this for every single part. So right here, I would find my left point and use that as my height. Bring it over and down. So my height here is going to be f at whatever this point is, times b minus a over n. Then do the same thing for this one. Use my leftmost point, or sorry, my left-hand point. Same thing. It's going to be f of whatever that is, times b minus a over n. And then for my last point, the same thing. F of whatever this point is, times my width, which is b minus a over n. Once I find it for each of these rectangles here, I'm going to just add those up. Okay? This is using left endpoints. This is left endpoint approximation. Using the left points on each part. Now I can do the same exact thing using right points. It's going to be the same thing using right points. So if I was doing right endpoint approximation, what I would be doing is still trying to find the area under the curve, right? So it's still going to look something like this from A to B, but this time when I split it up, I'm going to use the right points. So for this first part, instead of trying to find f of A, my height's going to be using this right-hand point, so it's going to look like this. So my height here is f of whatever this point is, and then my width is still b minus a over n. Same thing over here. Use the right-end point. So it's going to be f of whatever that is, b minus a over n. Same thing, use the right-end point, b minus a over n. And then the same thing, this height would be f of b now, times b minus a over n. Once I find what each part is, we can just add those up. So let's practice doing just this. Okay, let's practice this. Example. Use both right and left endpoints, endpoint approximations to approximate the area under the curve f of x equals x squared from x equals 0 to x equals 2 by splitting the area into 4 parts. All right, so I'm going from 0 to 2. So on the number line, I'm starting at 0 and I'm ending at 2. I don't care about anything else, okay? Now I'm splitting this into 4 parts. So, just like that, 1, 2, 3, 4 parts. So what I want to know is what are the x values for each of these, okay? So if I'm splitting this into 4 parts, the total length is 2. Splitting that into 4 parts, each piece is a half. So my next point would be 1/2, and then 1, and then 3 halves, and then 2. This is having it split into 4 parts. So let's start with the left side. If I'm using the left side, I'm going to use an L, and it's being split into 4 parts, so I'm finding L 4. So if I'm using the left points, my height right here would be whatever I get by plugging in 0, because I'm using my left point, right? So f of 0, and I'm going to multiply that by the width. Well, I can see here my width is 1/2. I know that because I'm going from 0 to 2, which has a total length of 2, and I'm splitting it into 4 parts. So each part has a width of 1/2. So f of 0 times 1/2 plus, for my next piece right here, my left-hand point is 1/2. So f of 1/2, and again my width is 1/2, plus my left-hand point on this one is the 1. So f of 1, and then again my width is 1/2. And then on my last piece, my left-hand point is 3/2. So f of 3/2 times my width, which is 1/2. So now I just have to find what all of those are. Again, what I did was, since I'm using the left side for each piece, each of the 4 here, I'm using the left-hand point. So 0, 1/2, 1, and 3/2. I don't use 2 because 2 is on the right side, and I'm using the left-hand points. F of 0 is 0 squared, which would be 0. F of 1/2, 1/2 squared is 1/4 times 1/2. F of 1 is 1 squared, which is 1. F of 3/2 is 3/2 squared, which is 9/4 times 1/2. So for the first one, I get 0 plus 1/4 times 1/2 is 1/8. 1 times 1/2 is 1/2. 9/4 times 1/2 is 9/8. I would need a common denominator of 8. So 1/8 plus 4/8 plus 9/8. 1 plus 4 is 5 plus 9 is 14. So 14 over 8. That's what I get if I use the left-hand side. So now let's do the same thing for the right-hand side. So this is going to be R4. So for my first part, the right-hand side is this 1/2. So we're doing f of 1/2 times my width, which is 1/2, plus, for this part, my right-hand side is 1. So f of 1 times 1/2. For this third part, my right-hand side is 3/2. So f of 3/2 times 1/2, plus, and then on this last part, my right-hand side is a 2, so it's going to be f of 2 times 1/2. Again, I wouldn't use this first point because that's on the left side. I only want the right-hand points. F of 1/2 is 1/2 squared, which is 1/4. F of 1 is 1 squared, which is 1. F of 3/2 is 3/2 squared, which is 9/4. And then f of 2 is 2 squared, which is 4. 1/4 times 1/2 is 1/8. 1 times 1/2 is 1/2. 9/4 times 1/2 is 9/8. And then 4 times 1/2 is 2. I need a common denominator of 8. So 1 over 8 plus 4 over 8 plus 9 over 8 plus 16 over 8. 1 plus 4 is 5, plus 9 is 14, plus 6 is 30. Sorry, plus 16 is 30. 30 over 8 reduces to 15 over 4. So again, explaining this makes it sound hard. It's really not. First, I just use all the left-hand points, so 0, 1/2, 1, and 3/2. And then for the right-hand side, use all of the right-hand points, so 1/2, 1, 3/2, and 2. If it helps you actually draw these out like this by parts, and then be like, oh, I can clearly see now the left-hand side of this first part is right here. The left-hand side of this part is that half and all of that stuff, if it helps. All right, let's do one more example. Approximate the area under the curve f of x equals 1 over x over the interval 1 to 2, and I want you to use n is equal to 4. What I mean by this is I want you to split it into 4 parts, is what we mean there. So again, let's look at the number line. I'm going from 1 to 2, and I'm splitting it into 4 parts. So this means if the total length is 1, right, from 1 to 2 is 1, but I'm splitting it into 4 parts, each gap is worth 1 over 4. So this would be 5/4 then. This would be 3/2, and this would be 7 over 4 here. Again, because each one is worth 1/4. So for the left-hand side, I would start with a 1. So f of 1 times 1/4, because that is my width, plus then 5 over 4 times 1/4. F of, next would be 3/2 times 1/4. And then lastly would be 7/4. Again, because I'm using all of the left-hand points. So the left for each part. 1 over x, remember what's really nice about that is I can just flip the fraction, right? So f of 1 would just be a 1. So 1 times 1/4. F of 5 over 4, I can just flip it and it makes it 4 over 5. F of 3 over 2, again, I can just flip that, so it's 2/3. Same thing with 7 over 4, I can just flip that, 4 over 7 times 1/4. Multiply that out, 1 times 1/4 is 1/4. 4/5 times 1/4 is 1/5. 2/3 times 1 over 4 is 1 over 6. And then 4 over 7 times 1 over 4 is 1 over 7. And if you add all of that up, get a common denominator and all of that stuff, you get 319 over 420. Now do the same thing using the right-hand side. R4 is equal to, now I'm using all of the right points. So 5 over 4 is first, times 1/4. Plus, then do 3 over 2, then do 7 over 4, and then do 2. Again, because I'm looking at all the right-hand points. F of 5 over 4, again, just flip it because it's 1 over x, so it can just flip. 4 over 5 times 1/4. F of 3 over 2 is 2/3. F of 7 over 4 is 4 over 7. And then f of 2 would be 1 over 2. 4/5 times 1/4 is 1/5. 2/3 times 1/4 is 1/6. 4/7 times 1/4 is 1 over 7. 1/2 times 1/4 is 1/8. Add all of those up. 533 over 840. So this is how I get really close to knowing how much space is under a curve. What I will learn in sections 5.2 and on is how to find what the exact will be.